Hello geometers, this is Miss Backfish and I am here to do some density practice problems with you today. Now when we talk about density, we're generally talking about one of two things. One is population density. If we're talking about population density, then it's the population, and that can be number of people, number of squirrels, number of, I don't know, however many things you have over the area. Okay, so like two-dimensional area, like area of a rectangle or a circle or a square or a triangle. All right, and you might not even know what the shape is. They just might tell you what the area is. Then there's also density equals mass divided by as solving for density. Like you could think of it as this equation, but this also helps you to see other ways the equation could be arranged. Basically, if something's over something, that means division, and if it's beside, that means times. So in other words, or if you need to find the volume, that's the mass divided by the density. Or if you need to find the mass, that means you're going to multiply density times volume. Okay, so that's just a sort of a little handy tool for thinking about the equation in different respects. So number one here says, as of 2015, the most densely populated state in the U.S. was New Jersey. The 2015 population of New Jersey was 8,957,000. This is a population they just gave me, okay? So this is my population, all right, with 1,219.1 people per square mile. All right, when you see per, that can be a helpful hint that you're talking about density is always something per something. Per is like division. So it's amount of mass per unit of volume, or population, number of people per square mile, or something like that. So that's what this is saying, people per square mile. So that's the population density. So here's the density. Now this is clearly about population. So this is the situation we have here. Population density equals the population divided by the area. What is the approximate land area? So we're trying to solve for this down here. So this is what we don't know. So there's going to be an X on the bottom on the right hand. So the population density, that's this, equals the population, which is this number right here, so that M on top, over the area, and that's the thing we're trying to find. We don't know. We'll go ahead and call it an A for area. So this is the equation that I'm trying to solve. So the first thing I would do is try to get the A out of the denominator. So we multiply both sides by A. And we could write it this way. But I'm going to do some. Alright, so I have 12,919.1 times A equals, and then let's see here. Is A alone yet? A is not alone yet, so I got to keep going. If I could focus a little bit better, sorry about that. Okay, A is not alone, so I have to get it alone, so that means dividing both sides by the plus and the minus like that. And then I'm ready to go to my calculator because A is alone. So I'm going to divide 8,957,907 people divided by that density, and I get 7,347.96. Now it says to the nearest square mile. That means a whole number. So 7,348 square miles, because it's area, so area is always squared units. Alright, next up, this one is kind of a weird question. It says the average amount of pasture that the user currently uses is 1 acre per year. And then it tells me about 3 pastures at this farm and tells me that they're going to be getting 6 mules. And right now, the farm does not have enough pasture space for 6 mules. So they want me to tell them what is the least amount of additional square footage that we need to add to these 3 pastures in order to have enough square footage. So there's different ways to interpret this. Like, are these pastures adjacent, or do we have like, a pasture, and then there's a stream, so we don't want to fence the stream, and then there's pasture over here, and then there's a road, and then a pasture over here. Okay? If the pastures were not adjacent like this, that would kind of make it a more complicated problem, because what if this pasture is big enough for 2.3 mules? Well, we can't put a point 0.3 mule here, so then we'd only be able to put 2 mules here. So we'd have to put another one over here. And it just gets into a little bit more complicated scenario. So what I'm going to do is I'm going to interpret this part of the problem. What is the least amount? As being my permission to say that these fenced pastures are not only next to each other, but I can move the fences if I want to. In other words, what's the best case scenario? Is that it's just wide open land and I can change these rectangles as needed. Okay? So, first I need to figure out how many square feet we have right now. So I've got one pasture that's 100 by 300, one pasture that's 150 by 500, and one pasture that is 250 by 400. Keep in mind that you want to pause the video at any time and figure out the next part, or figure out just what we're looking at right now. Feel free. That can be helpful. Okay, so this is what we've got right now. 100 by 300 is 30,000 square feet, 150 by 500 is 75,000 square feet, and 250 by 400 is 100,000 square feet. That all adds up to 205,000 square feet. Now this next part, that's just kind of, this is not really me asking a question. Just out of curiosity, I was like, well, if we don't have enough space to put 6 mules yet, how much space do we have? We have enough right now to fill in here. So let me talk to you about how I got that. Okay, so we have a total, and I'm just going to put this number down just to have it on hand. Right now, we have a total of this many square feet. Now, we want to be able to stick 6 mules. Each one mule needs a whole acre of grazing land. Conveniently, they told me how many square feet are in an acre. That's convenient because all of these are in square feet. So let's just go ahead and think of it as in square feet. So instead of saying we need 1 acre per mule, I'm going to say we need this many square feet per mule. Okay, so that's the same thing. So if I need that many square feet each per mule, and I want to be able to accommodate 6 mules, then I'm going to multiply 43,560 square feet times 6. And I'm going to need 261,360 square feet. This is how much is needed for me to correctly house or correctly supply for 6 mules. We already said this is how much we have. So when they say what is the least amount of additional square footage, I'm just going to subtract. That's all I've got to do. Additional means how much more? So we need 21,360 minus 2,000. And that is 56,360 square feet. So if the pastures were arranged perfectly so I could easily add the amount I needed, in other words, I didn't have to add more than I needed because of the river handling, then this is how much additional grazing land I need before I get those 6 mules on my list. Alright, moving on. And again, remember, you can pause this video at any time to try problems, or if you're like, oh, I missed that part, now that she said that, let me go back and try it again. Number 3 says 98 cut boulders are being brought in to help prevent further erosion on a portion of the coastline. Each boulder has been roughly cut into a tube with sides of length 0.8 meters. This part right here is a hint to us that we're going to need to find volume. Anytime a geometric shape, a geometric solid, is mentioned that is not two-dimensional. Now up here, we have rectangles. Rectangles are cubes. That's area, okay? Down here, here's the three-dimensional. They're like rectangular prisms or spheres or cylinders. That's when we talk about volume. So this is going to be one where I'm going to use this relationship. I'm going to be talking about mass and volume. That's what that tells me. So I'm going to need to know the volume of my cube. So I might as well go ahead and find that. Volume of a cube. Remember, volume of a rectangular prism is 1915 height. With a cube, they're all the same. So that's 20 times 20 times 20 or 20 cubed. That's why we call it a cube. So 28 cubed gives me, let's say 25 times 2, and the units are meters per cubic meter. So that's how much volume there is in each cube boulder. Boulder cut into a cube. Okay? That's the volume per boulder. Then it says the stone in the boulder has an average density. So there's my density. D is 3,000 kilograms per cubic meter. Again, I'm going to go ahead and start this out in practice. So this is what we've got. We know the volume, we know the density, and they're asking me for the mass. It says find the weight or mass for each boulder in the cabinet. Round to the nearest tenth of a pound. According to this, if I want mass, that's density times volume. So density is 3,000, volume is 0.512. Those two numbers get multiplied. So 3,000 times 0.512, that gives me 1,536 for mass. Mass is 1,536. Now this is where things get dicey. The units here, I multiply density times volume, and let me just show you, we can actually work things out on the screen. So I'm going to multiply the density. So density was in kilograms per cubic meter. That means this. So that was my density. I multiplied it times the volume, which is in cubic meters. Okay, you can deal with the units just like you would numbers. So this is kilograms times cubic meters on top and just cubic meters on the bottom. So the answer that gave me is in kilograms. When I multiplied those numbers, that gave me an answer in kilograms. So the mass right now is in kilograms. They want me to give an answer in pounds. Okay? So that means I need to convert it. Please don't forget that you have a wonderful thing called Google or Bing or whatever you want to use. You have your phone. So if you're not sure how to convert kilograms to pounds, you can just type convert kilograms to pounds. We could type in pounds, or the abbreviation is LBS. Okay, 1 kilogram is equal to 2.2 pounds. All right, so going back to what I've got, each one of these kilograms is 2.2 pounds. So I'm going to do 1536 times 2.2 to see how many pounds I have. And I get 3,379.2. It says round to the nearest tenth of a pound, so that's actually what we just had. So 3,379.2 pounds. So that is my answer. Finally, a dump truck with a carrying capacity, and I say finally like it's the end of the problem, but this one actually has some, its own stuff to work out. A dump truck with a carrying capacity of 28,000 pounds is used to transport the boulders to the coastline. How many trips will the truck need to make? Okay, assume the truck does not exceed its carrying capacity. So that means we can't take, this is the most poundage we could take. We can't take more than that. All right, A boulder is not something you can cut in half. You can't have a third of a boulder, because if you have a third of a boulder, you actually have a smaller boulder. All right, so we're talking all of these cubes need to stay intact. So if let's say I want to do, let's say I want to carry 6 boulders, okay? Each boulder weighs this amount. So 3379.2 times 6. Could I do that? Yeah, that's less than 28,000. So I've still got some more room, so let me add another boulder in there. So maybe 7 boulders would be a good amount per load. Well, 23,654 is still less than 28,000. So yeah, we could do 7 boulders in each load. Maybe 8. So 3379.2. Looks like we can carry 8 boulders per load because this is 27,000. That's how much 8 boulders weigh. And we can carry up to 28,000. What about 9 boulders? No, we are now over 28,000 pounds. So we can't carry 9 boulders. The most boulders we can carry is 8 boulders. 8 times 3379.2. Even though there's leftover space. There's almost 1,000 pounds of space left, but we don't have 1,000-pound boulders. We've only got boulders this big. So 8 boulders is the most we can carry in each load. All right, now we need to know how many of these boulders do we have to carry? 98. We have to carry 98 of these. You can't just multiply 98 times this amount and then divide by 28,000 pounds, because that will have us carrying parts of boulders in a load. Okay, we have to make sure we can fit a certain number of whole boulders in each load. And we have figured out that a dump truck load, the full load for our purposes, is going to be 8 boulders. That's the most we can carry. So if we have to carry 98 boulders, we're going to do 98 divided by 8, see how many times we have to make a trip. And the answer is 12.25, except you can't just take a quarter of a trip. That's basically almost like saying that on the last trip we've only got quarter of the capacity. So we really need to take 13 trips. Because after 12 trips we won't be done. We'll still have some boulders left to pick up. All right, that was number 3. Moving right along. Number 4 says an air conditioner is being purchased for the room shown at the right. The room has an open ceiling that follows the roof trusses. That's just a way of saying it's like triangular at the top of the room. According to the U.S. Department of Energy, to determine the cooling requirement of a room, use 2.5 BTUs per cubic foot of airspace. If you're curious about what a BTU is, that would be another good thing to Google. I'm not curious enough to do it right now. 2.5 BTUs obviously is a measure of how much energy you put into cooling, but 2.5 BTUs per cubic foot. So we need to know how many cubic feet this is. This is a composite geometric solid, meaning it's more than one put together. We have a prism on the base, and then above it we have another prism. This is a rectangular prism. We have another prism. We know it's a prism because it has 2 matching polygons that are parallel to each other. And those tell us what type of prism. So the top is a triangular prism. All right, so I'm going to go ahead and pause and draw these real quick. Okay, so here are the 2 geometric solids I have in that picture. And I kind of turned the triangular prism a little bit so that I could see the end a little better. It's not the best drawing ever. Hopefully that you can see how that's the same shape. Okay, so I put my measurements on each one of these. Notice that this triangle here is 18 across. Sorry. 18 across, just like down here. So I put it's 18 across. And then the height is 6 feet. The height goes right down through the middle of a triangle. All right, so we're trying to find the volumes of this prism and, this rectangular prism and this triangular prism, and then we're going to add them together. So you might want to pause and do it now. All right, volume of a rectangular prism is just length times width times height, where you multiply all the dimensions. So 24 times 18 times 9 gives me 3,888 units. I think they are feet, cubic feet. Okay. Now then over here, volume of a prism, you can think of it as area of the base times the height. Well, the base here is a triangle. This is my base. Okay, area of a triangle is always 1/2 base times height. In other words, base times height of the triangle. So we're looking at this triangle on the end. If I want the area of this triangle, the base of the triangle is 18, the height is 6, the area of this triangle is 1/2 times 18 times 6. 1/2 of 18 times 6 is 54. So in my volume formula, if you have that big B, that's what that is. The capital B doesn't just mean base, it means area of the base. So this is the area of my triangular base. Now, height in a prism is also something you got to think about. Height is not up and down. It's not going to be the 6. The height of that's the height of this triangle. It's not the height of the prism. Height of a prism is the distance between the two bases. So this is 24. So my volume of that triangular prism is 54 times 24 is 1,296 cubic feet. So now I have both of these numbers. The room is those two shapes put together, so I can add them to find out how many cubic feet are in the room total. And my total cubic feet for the room turns out to be 5,184 cubic feet. So 5,184 cubic feet. 5,184 cubic feet. This is the room. All right. So I need to use 2.5 BTUs for each one of these cubic feet. So that means this is going to tell me how many BTUs I need, or at least so far, based on what we know so far. So that gives me 12,960 BTUs. Now here's the thing. This part right here, to this value add an additional blah, 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 blah. This is pointing out to me that windows make it harder to heat or cool a space. If you have a window, cold air gets out through the window or comes in through the window, hot heat goes out or in, basically whichever one you're trying to keep in goes out, and whatever you're trying to keep out comes in. Okay, a window is not as good as a wall for keeping the air inside the same temperature as you want. So to this value, that's the value we just got, add an additional 1,000 BTUs for each window, and this room has 4 windows. So I'm going to add 1,000 4 times, or 4,000. Since I wrote it that way, I'll just keep writing it that way. Okay, so I'm adding 4,000, so that's going to be 16,960 BTUs. This is something that we would actually calculate because we would need to know how big an air conditioning unit to buy for this room. All right, last problem. In the movie Raiders of the Lost Ark, archaeologist Indiana Jones replaced a solid golden idol with a bag of sand. The idol rested on a platform which precisely counterbalanced the temple's ancient self-destruct mechanism. The idol can be modeled by a cylinder with a height of 18 centimeters and a radius of 6 centimeters. The density of gold is 19.32 grams per cubic centimeter, and the density of sand, not then, it should just say the density of sand is 1.6 grams per cubic centimeter. All right, feel free to skip this, but I'm going to give you a frame of reference and show you that scene, or at least part of it. Okay, so at this point in the movie, he's gone down through this like cave that was booby-trapped in all kinds of different ways to get to this statue. Okay, so that's a really epic scene in a really good movie, and he has a great deal of trouble getting out with things falling apart like that. So it's worth watching. But what was the mass or weight of the idol in pounds? Okay, so it was a cylinder, could be modeled as a cylinder. It wasn't really one, with a height of 18 and a radius of 6. So the volume of a cylinder is, let's see, area of the base times the height is pi r squared times the height. So pi times radius squared times height. Okay, so that gives us 648 pi. I'm going to leave it in terms of pi for a second. And then I need to know the mass. And I'm going to use this because I know the volume now. And they told me the density. The density of gold is this. So now that I know the density of that statue, because it was gold, and the volume of that statue, I can multiply those two numbers, 19.32 times the volume. And I'll go ahead and change it to a decimal when I do that. And I get 39,330.7. Now, is that pounds? How could you pick up something that's that heavy? 39,000 pounds? No. This was cubic centimeters because it was centimeters. And then the density is in terms of grams, G, over cubic centimeters, grams per cubic centimeter. So again, that can tell us, since we multiplied cubic centimeters times grams per cubic centimeter, the cubic centimeters cancel and just gives us grams. So this number is in terms of grams. All right, so I need to figure out what the weight is in pounds. So again, I need to go convert grams to pounds. So let's go ahead and hit up Google. And I'm going to type convert grams to pounds. 1 gram is this amount of a pound. A pound is bigger than a gram. So for each 1 gram I have, I'm going to multiply times, and you don't want to round this much because that's a very small number. You want to be as precise as you can. So I'm going to go with 0.0022. Okay, so for each one of those grams, I'm going to do times 0.0022. And that gives me about 86.5 pounds. 86 pounds is a lot for that little statue. And if you think about how he handled it with one hand, no big problem, that's pretty surprising. So let's look at the sand he brought and what the weight of that sand would be. Okay, the density of sand. Let's suppose that we bring the exact same volume of sand, like the sand is in the same basic shape and size as the cylinder. Okay, so volume of the cylinder was this. Okay, actually, I'm sorry, we don't need to do that. We need to figure out how much. We need to look at it a different way. We need to know what is the needed volume of sand to avoid tripping. So in other words, how much sand would be 86.5 pounds. Now remember, this is mass. So we're looking at 86.5 is my mass. Density here, we know the density of sand is 1.6 grams per cubic centimeter. And they want to know in cubic centimeters, what's the volume? Now, don't forget, this is grams, this is pounds. We really need to think back in terms of grams here. So let's put this in terms of grams on top. So this number, which is right here, over this number will tell us the cubic centimeters. So 39,330.7 divided by 1.6. So the volume of sand needed was 24581.7 cubic centimeters. Okay? 24581.7. That's a pretty big amount of sand. All right? Let's think about what that means. 24581. Let's just do 2458. Let's divide that by 1,000. Okay, so like if I had a box where oh boy, I'm not doing very well with this box, where the base of the box had a length of 1,000 centimeters, then the height times the width would have to be 24. So let's just think of, what if the height was only 1 centimeter? 24 centimeters. Okay? 1,000 centimeters is like, 1,000 centimeters is like about 10 yards. Okay? So 10 yards is like 1/10, one section of a football field between the lines, between the big lines. So we're talking about a box that big, that long, and then 24 centimeters wide, which is like, just imagine it being like a foot. The point is, that little bag he had is nowhere near this many cubic centimeters. And the funny part is, he actually took sand out, like he thought that was going to be too heavy. So, is that scene realistic? Absolutely not, based on our calculations. And really, you can see that kind of based on the density here. If you just look at the density, the gold density is 19.32, sand density is 1.6. That bag and that statue were almost the same size. But two things that are the same size, if one's made of sand and one's made of gold, the gold would weigh almost 19 times as much, like 17, 16 times as much. So, yeah, that's not going to work, but he tried. Then again, in the movie, it also did not work, so it's somewhat realistic. Thanks for watching. I hope this helped, and I will see you later.